probably want this discussion recorded. So, I would, hopefully the people that are watching the recorded lectures, listen to this. I'm kind of talking to them, not to you who are here, but I really hope I start seeing more people here. I just know that attendance is just very highly correlated with success in this class. So if you're not physically attending, I strongly encourage you to. But like Friday, if the weather is really bad, I mean, I'll have the recorded lecture posted after class. I don't want you to like be on the roads if you're driving an hour, driving from Indy or something, and the roads are real bad. I don't want you on 69 going over here. So I completely understand if the weather gets too crazy here over the next 24, 48 hours. I understand about Friday. Yeah. Actually, I think I've only, all my time is either being a professor or back when I was in college. I only had college classes closed because of weather one time. And it was actually not because of snow, it was because it got so cold. So they're way more likely to cancel due to like negative 30-degree wind chills, because you guys are walking around, like they're not really thinking about commuters as much. And so you're less likely to get those cancellations because of snow, more likely with those really extremely like cold weather. But anyways, it's a little bit of an aside, but right. So off the top, I will have an online quiz though that I'll post after class today related to what we talked about. Just a couple little questions. They shouldn't be too difficult. That'll be due before we start class on Friday. You've got those other two Excel and Connect assignments due at the end of the day Friday. So if you have any kind of last minute questions as you're kind of working on finishing those up, feel free to reach out to me. I've got my office hours today. Even if we, for whatever reason, classes get canceled or something tomorrow, I'll be here. I am from Michigan and I'm used to driving in snow, so it doesn't bother me near as much, and I have plenty of work I need to do. So I'll be around typical office hours, or tomorrow, like if you get some gaps in your schedule, just shoot me an email. I'll be around most of the day. To start out, I want to go through, I still had this pulled up from the last section. So we left off here. We're going to start talking about probabilities today, but I wanted to show you some stuff in Excel. So a couple reoccurring questions I've gotten to Connect. I've realized I forgot to show you one thing in Excel when I was starting out kind of my introduction into it. So let's say I've got this small data set and I want to find the sample variance, right? So I use this var.s formula. So I have it defaulted so that it shows what, 5 decimals. When you download those files from Connect, I don't know why it does this, but it some reason switches the default on some of these to looking like, you'll notice here up on the home tab, there's these little kind of symbols here. And when I click them, it changes the number of decimals that it displays the value to me as. So if I make the decimal small enough, this rounds down to 1. But the answer isn't 1, it's 1.42, whatever that decimal was. But I can't see that because the formatting has changed. So the number stored in the cell is stored out to like whatever decimal it stops at. But the number displayed to you is different. So like on one of the connected questions, it'll look like an integer, but if you actually change the formatting, you'll see that it has decimals associated with it. And it often wants you to enter in up to the second decimal. So one way you could also do this is if you right click on a cell, even if it, whoops, wrong way. Even if it looks like an integer and you go to format and you click here at the number, you can change the number of decimals you want. And then you can actually see, oh yeah, there was some decimals associated with that answer. All right, so be careful when you're working through those. If you think you're using the right thing, like I'm using the var.s and it's still telling me it's incorrect, it's probably a formatting. It's just displaying the number to you without the decimals. Okay. Another kind of formatting issue we can run into is, let's say I've got like a relative frequency of 0.25. Okay. And maybe I want the percent frequency. And so I think, okay, I'll just click on this and they got a nice little percent thing. It'll just switch the number to 25 for me. Well, it's just switching how it's displayed. So it looks like there's a 25 stored in that cell. But if I use that cell anywhere else, let's say I try to multiply this by 10. It looks like I'm taking 25 and multiplying it by 10. But what's actually stored in that cell was that original decimal format, 0.25. So notice when I multiply that cell by 10, instead of getting what, 250, I get 2.5 because it's using the value that's stored in, and what's being shown to me is just a formatting change. It's just displaying it differently. right? The actual value that's still stored in there is 0.25. Okay. So be careful. Like I always kind of say, I know like in accounting, they like to use the dollar formatting because everything's in dollar. I just like to say, don't play around with the formatting in Excel unless you're trying to give like a visual presentation. When you're just working with the data, don't mess around with the formatting. You want to see what the actual value that's being stored in that cell is. Okay. Any questions on anything there before we keep moving? Or any questions you've had kind of running into Excel, anything weird? Okay, so we'll jump into the next topic, which is basically probability, right? Now we've kind of already talked about this a little bit, so I can relate this to some things we've already went over. But really, when we're talking about probability, the way we usually say it in kind of our everyday language is, what are the chances that something occurs? What are the odds an investment becomes profitable? What's the likelihood, something is increases productivity, right? So all these words, terminologies, really, we're trying to get at, I've got something that's uncertain. I know that there's a variety of different outcomes that could occur, and I want to know what's the likelihood, what's the chances, what's the odds that any associated with each one of those possible outcomes. So what we're going to start thinking about, we'll go through some terminology. We'll start thinking about these uncertain events, right? These events that have uncertain outcomes, we're just going to call them experiments. Excuse me. So these experiments are not like a physics experiment, or not with beakers or Bunsen burners or anything. It could literally just be selecting a person at random and asking what their age is. Excuse me. Okay. So, as long as I'm just selecting a person at random in the same way, I'm running this experiment over and over and over and over again. I'm selecting a person at random, asking what their age is. Selecting a person at random, asking what their age is, right? So I've got all these different experimental outcomes that I could see this experiment take on. So when I select somebody at random and ask them their age, I know that's going to be somewhere between 1 and, or I guess 0 technically, and however the oldest person that's ever lived has been, right? Now, when I select that person at random, if I visually can't see them, maybe it's just like sending them something via the internet. I don't know what they're going to respond with, but I know it's going to be somewhere between 0 and 150 or something, right? So we'll call those experimental outcomes, every possible outcome we see, that's our experimental outcome set. Now, if we only, if we don't run this experiment a lot of times, sometimes we'll have this, the outcomes that we see this experiment take on, we won't see every single possible outcome. So imagine I'm rolling a dice, right? It's got 6 sides, and I don't have any idea what the numbers are. So maybe it's not 1 through 6. Maybe this has 6 random numbers, right? So maybe one side's 42, the other side's 29, right? 6 random numbers, and I don't know what they are. Well, if I only roll this dice twice, I'm only going to see 2 of those sides. Right? Let's assume like when I roll it, maybe someone else is rolling it and telling me the number. Well, if they only roll it twice, I only know 2 of the possible 6 outcomes. So sometimes if I don't run my experiment enough, my sample space is going to be a little bit smaller than my experimental outcomes, right? Now, if I roll this dice 200 times, I'm going to see every single side, right? And so if I run the experiment enough times, usually my sample space is just as large as my experimental outcome space. But if I don't, it could be a little bit small. Usually we're going to talk about events that are within this entire experimental outcome space, but we're only interested in a few of them. So maybe rolling a regular 6-sided dice, maybe my event is I'm just interested in, is it a 2 or a 3, right? So it's a small subset of the possible outcomes that I could see. So we'll mainly think about, I don't use the sample space. We don't generally have to talk about too much because we usually have huge data sets. We've usually got experiments that have been run several times that we can kind of look at. So a nice visual of this is like, here's all of our experimental outcomes. This space just represents, rolling a 1, rolling a 2, rolling a 3, like all the possible outcomes. Our sample space are just going to be what outcomes we see from running the experiment. And then within that, we might be interested in a small subset, just getting a 2 or just getting a 6 when I roll this dice. Okay. So experimental outcome space, sample space might be a little bit smaller, and then whatever event we're interested in, probably a much smaller subset of the entire space. Okay. Questions to this point? Shouldn't be anything crazy yet. Okay. So, we can think of different experiments, flipping a coin. What are the possible outcomes? Heads or tails? Rolling a regular, dice, not Dungeons and Dragons dice, just regular six-sided, 1 through 6. Right. Choose a card from a deck. If I don't worry about suit, I'm just interested with the face card and what the card is. Ace through king. Playing a postseason football game, win or loss. Regular season soccer game, win, loss, or tie. So these are all, just a variety of different, experiments. Like anything can really be an experiment as long as it has an uncertain outcome, right? And we might be interested in things like, these ones are a little bit easier to think about. What's the probability I roll 3? Well, what's the probability that I lose the game, right? We can assign probabilities to all of these different outcomes, okay? So how do we assign these probabilities? We'll talk about that in just a second. But before we do, let's think about some of the characteristics of these probabilities, okay? So the probability is just going to be the likelihood that we see a certain outcome when this experiment is run. You can really think about it very similarly to proportions or relative frequencies, right? So you can think about it this way. If I were to just sit here and roll a dice and record like what the outcomes were, actually, does anybody know what the game Settlers of Catan is? Have you ever played this? Oh, this is a really great game. It's really fun. So anyways, I mean, it's like probably not maybe, but I enjoy it. So actually, I was playing with my wife and I think I'm crazy now, I think, but I literally just like recorded every roll of the dice. And if you roll this dice enough times, what you find out is the proportion of times you roll a 1, if you look at a large number of rolls, ends up being about 1/6, right? The proportion of times a 1 comes up is 1 out of 6. The proportion of times a 3 comes up is 1 out of 6, right? Now, so those are proportions, but that's basically also the same thing as saying the probability I roll a 1 is 1 out of 6. Right? So proportions or probabilities, we can kind of think about these very similarly. Right? So what's the lowest a probability could ever be? What did we say the lowest that a proportion could ever be, or lowest a relative frequency could be?
0.
Yeah, if something just doesn't occur, the probability is 0. What's the highest it could ever be? A guaranteed chance of occurring? 1. This is where we gotta be careful, right? There's 100% chance it occurs, but the probability it occurs is 1, right? So here, kind of thinking about if I've got this experimental outcome E, the probability that it occurs has to be somewhere between 0 and 1, and it technically could be 0 or 1, right? Those that, we don't have a lot of situations like that. Otherwise, we don't really have to do a lot of analysis if we know the probability is 0 or 1, right? So I think, what did I skip over here? Oh, sorry, the probability of an event, another thing I want to mention. So if we had the probability of this event, it's somewhere between 0 and 1. The probability of any one outcome. The probability of an event, you would just take every outcome in that event and add them up. So for instance, the probability I roll a 2 is 1 out of 6. The probability I roll a 3 is also 1 out of 6. So what would the probability of the event that I roll either a 2 or a 3 be? Well, I just add up the probability of each event. 1/6 plus 1/6 would be 2/6. That's nothing too crazy. So we know it's between 0 and 1. We also know that if I took the probability of every possible outcome and added them up, what should that add up to? It's kind of similar to what we said when we added up the relative frequencies, those should always add up to 1. Think about it this way. Each number on the dice has a chance of 1/6 of occurring. So if I add up 1/6 across all 6 outcomes, 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 would add up to 1. Right? So if we take the probability of every possible outcome and we add them up, they should always add up to 1. And we'll use this, I think we'll give you kind of a visual of this as well here in just a little bit. All right. Any questions up to this point before we keep moving? And I'll probably go through this next little part kind of quick. It's not overly important, but we want to have some basis for where these probabilities are going to be coming from that we'll start looking at. Oh, wrong arrow. So we've got 3 ways of assigning probabilities: classical, empirical, subjective. I'll go over each one in more depth here right now. So, excuse me. The classical probability is probably the easiest, right? It's just everything is equally as likely. So this was where I said rolling a dice, everything's equally as likely. The probability of any one number was 1/6. If I flip a coin, the probability I see heads or tails is 1/2, right? If I flip a coin twice, the 4 possible outcomes, I could get 2 heads, a heads then a tails then a heads, or 2 tails. So 4 possible outcomes, all equally as likely. Each one has a probability of occurring of 1/4. So how am I getting these probabilities, right? When it comes to the classical method, if everything is equally as likely, and we'll call any outcome here just, outcome A. So whatever outcome we're interested in, if everything's equally as likely, with the classical method, the probabilities would just be 1 over the number of possible outcomes. Kind of representing that with n here, but the number of possible outcomes, 1 over that, that's going to give you the probability of each outcome occurring if everything's equally as likely. That would be using the classical method. Okay. Any questions there? That one shouldn't be too, I think this one like makes sense. And usually the examples, it's very obvious that we should be using the classical method, like rolling a dice or drawing a card from a deck, something like that. The next one, which is probably what we would use 90+% of the time, is going to be the empirical method, right? So kind of the setup I have for this one, I'll give you the example and go over a little bit more technical details. So let's say I'm choosing someone at random and I'm interested in what's the probability that their favorite cuisine is Mexican food. Right? Well, I don't know anything about this person, but I've got a set of 60 people. And in this case, I have a class of 60 students I was thinking about, and I asked all of them, right, each one of them what their favorite type of food is. And I find that 15 out of the 60 responded Mexican food. So if I use that old data, historical data, the times that I've run this experiment before, just asking a person what their favorite food is, I know that based off of history, there's a 15 over 60 or 0.25 probability or 25% chance that they respond with Mexican food. And so that's the probabilities that I'll use moving forward. And then, maybe over time, as I ask more people, maybe I update those probabilities with the new data, right? But I am using data on when this experiment has been run in the past to predict what the probabilities are for the future. Right? I mean, this is the majority of what we try to do in like every business tries to do, right? I try to use old data when they've done things in the past to adjust or to make more optimal decisions for the future. Okay. Any questions on this one before you keep moving? And I think this will make a little more sense. So Friday we'll do a little bit of Excel work, or at least I hope we get to the point where we'll do some Excel work. And I'll show you how we start to come up with probabilities based off of some old historical data. Or I shouldn't say historical, it makes it sound like, but we're looking at one that an experiment has been run in the past. The last one is going to be the subjective method, right? So this is just where we assign probabilities based off of some expertise, some knowledge about the subject. And it usually applies to situations where we just can't use the other two. Right? So maybe a company is going to hire a new CEO. They've got 4 different candidates. Well, it doesn't make any sense to run the classical method here to assign probabilities because, maybe this person has been the CEO or has been, CEO of 2 different successful companies. This person has bankrupted the last 3 companies that they ran. Maybe this person just graduated high school. Well, I know each one of those people have very different likelihoods or very different probabilities of getting the job, right? So I can't use the classical method. I don't want to say they all have an equal shot, right? But I can't use the empirical method either because I don't ever have this experiment run before. The same 4 people, same 4 candidates applying to the same position. I don't have any historical data on this experiment being run and what the outcomes were. So all I can do is, use, some industry expert to kind of look at these resumes and try to predict the probability, try to assign probabilities of which one they think is more or less likely to get this job. So this one seems a little bit hokey, right? But usually it applies to situations where this is just the best we can do, right? We can't use the classical method. We can't use the empirical method. Those don't make sense in the context of what we're trying to do. And so all we can do is use our expertise or our knowledge. And maybe we can look at other quote unquote data from other candidates to try to get good predictions, but we don't have any data on this very, same specific experiment being run, the same 4 candidates applying to the same job. So welcome to probability statistics, where everything's made up and the numbers don't matter, right? That's kind of what the subjective method feels like, but it's just a situation where that's the best we can do. And if you haven't ever seen Whose Line Is It Anyways, search it on YouTube, try to find the oldest clips. Those are some of the best ones. I highly suggest it. I've won a few YouTube spirals before. So we've got this idea of probability set up now. Okay. We're going to use a little bit of what I'm going to call, it's not perfect, similar to set theory, right? But I'll start giving you some ways of thinking about numbers, and I'll also give you visuals for some of the things that we're going to want to find the probability of. So the first is the complement of an event. Okay? So when we write A with a superscript C, that means I want the complement of event A. Okay? So let's give some numbers that are, actually put some context to this. So let's say event A, we'll use rolling a dice. I think that's an easy one to think about. So let's say in event A, the outcomes that are in event A are rolling a 1, 2, or a 3. Okay. A complement means every outcome that's not in event A. So what's every other outcome we could see from rolling a dice that's not in event A here? Yeah, just the other numbers on the dice that aren't included in event A. What if I had event C? Let's say event C is just seeing a 6. What would C complement be? Yeah, just every other possible outcome. Okay. So the complement is just every other outcome that's not in the event that you're finding the complement of. Okay. So here I'm going to write another event down for the next thing we're going to talk about. So let's say event B is either a 3, a 4, or a 5. Those are the possible outcomes in event B. The first thing we're going to think about is finding what we call the union of two events. Is it in A or is it in B? Right? So we've got the union of two events means is this outcome in event A or is it in B? It can be either one. Now, it could be in both. We don't really care, but it's at least in one of them, right? So what are the outcomes that would be in event A or in event B here? Well, the outcomes that are in A, 1, 2, 3. And then the outcomes that are in B, we've already got the 3 recorded. And then 4 and 5. So all the outcomes that are in either A or they're in B is 1 through 5. All right. So there we're just kind of looking for what numbers would be in both events. So, this union, we usually say like it's A or B, right? And the way to kind of remember is like, this is actually not a U. This is actually a set symbol, right? So it looks like a U because I can't draw the difference between the two, but it really is a set symbol. But it's kind of nice that it looks like a U because it's a nice reminder that this represents the union. Is it in A or is it in B? Okay. Any questions up to this point around that? Okay. The next thing we might be interested in is the intersection of two events, or this upside down set symbol, which kind of looks like an upside down U. This means, is it in A and in B as well? So it has to be in both of them, right? So what outcomes would be in A and B here? Yeah, the only outcome actually that's in both is 3. Another way of thinking about this. What if I wanted to find B intersection with A complement, or B and A complement? The outcomes that would be in both of those, yeah, it looks like it's 4 and 5. So this is kind of how we want to think about it with numbers. I'll then kind of give you a visual with some Venn diagrams here in a second. But these are going to be primarily the things that we'll kind of focus on today, and we'll kind of be using moving forward. We've got complements, unions, intersections. Unions, another word is or. Is it in A or B? Intersections, A and B. Okay? And sometimes people say like, here's the U for union, but also like, if you like drew a line through this, it looks like A and B, looks like another A. I don't know. I don't really necessarily didn't learn it that way, but I've had people tell me that helped them. So it's another way of thinking about it. Okay. All right. So that gets the first 3 out of the way. The fourth one, I'll kind of save some of the discussion on till Friday. It makes a little bit more sense when we deal with some actual probabilities from a contingency table, but it's what we call a conditional probability. So this line, this vertical line, the way we would read this is A given that B has occurred, or A conditioned on that B has occurred. So it doesn't really make a whole lot of sense until we start talking about actual probabilities, but I'll kind of give a little bit of intuition behind why this conditional thing might matter. So maybe I'm interested in, okay, across like every day of the year, what's the probability that on any given day when I walk out of the building that I slip and fall? Right? I haven't done it yet, right? There is a probability associated with that. However, if I tell you, okay, what's the probability that you slip and fall, given that it's 32 degrees, rain, snow mix, now what's the probability that when you walk out of the building, well, now it's a lot higher, right? Once I have this additional information, okay? So sometimes this additional information, given that B has occurred, that'll change the probability that A has occurred, or that A is going to occur, sorry. And like I said, we'll talk more examples there kind of on Friday, working with conditional probabilities, but kind of just the notation, this vertical line, the way we read it is that A given that B has already occurred. So we're still interested in event A, but it's just we have this additional information that B has already occurred. Okay. All right, so some nice visuals of this, right? If I draw this rectangle to represent every single possible outcome, so it's my entire experimental outcome space, that rectangle should have an area of 1. So if I add up the probability of every possible outcome, yeah, they always add up to 1. So this rectangle representing every possible outcome means that that space is, we can think of it as a probability of 1, okay? Within that experimental outcome space, we've got event A that we're interested in. Now, event A could include several outcomes, right? But it could just be one outcome, it could be several, right? But it's going to be, a subset of the outcomes that are in our experimental outcome space. So visually, we're going to draw this probability of A, or all the outcomes in A, as kind of this circle. Same kind of idea for B. Now, if I think about if I had circle A and circle B, everything that's in both of them, that would visually represent my intersection, right? These are all the outcomes that are in both A and in B. Okay? And then here, if I think about the entire kind of space of all the outcomes that are either in A, or they're in B, or they're in both, this would kind of represent my union. I'm in one of the circles, right? I could be in just A, just in B, or I could be in both, right? But I'm in at least one of them, okay? Excuse me. So these are kind of the visual representations of the intersection and the union. And we'll break them down a little bit here in a second, because we want to put some actual numbers to these things, right? So the way we're going to do that is use something called a joint probability table or a contingency table, okay? So the way we read this table is that the total columns represent the probabilities of the events themselves. So for instance, the probability of A is 0.6. The probability of B is 0.5, right? Those totals just give me the probability of whatever the row in the column heading is, of the cell I'm looking at, so to speak. So the top 4 left cells, the top 4 left cells would all represent intersections. Okay? So the probability of A and B is 0.4. The probability of A complement and B complement is 0.3. Right? Or the intersections are all represented in those top 4 left cells. So when I'm thinking about these totals, and I think here I jumped the gun a little bit. So here's the slide, right? We can identify different intersections here in those top 4 left cells. For the events themselves, I said you can go over to the total column, but how could we maybe recreate if we weren't given these totals? We can actually add across the rows and down the columns to come up with the probabilities of these events. So notice 0.4 plus 0.2 is 0.6, 0.1 plus 0.3 is 0.4, 0.2 plus 0.3 is 0.5, right? Adding across the rows or down the columns would reproduce those totals. So why does that work? Okay, so I'll give you an intuitive description and then a visual. So let's say event A is that somebody wants marijuana legalized, right? And event B is that they're older than 65. Okay. So if I take everybody who wants marijuana legalized and is older than 65, and I add to that the probability that someone wants marijuana legalized and they're younger than 65, well, that covers every single person who wants marijuana legalized. So when I add those together, that just gives me the total probability of wanting marijuana legalized, right? So if I'm taking the probability of something and another event, right, the intersection of those two, I then take the probability of that event and the intersection with that other event's complement, those will always add up to just the probability of that event itself. Okay? So that's kind of the example that maybe a little bit more intuitive. And I want to think about the visual. So if I've got two events, so A and B here, and I'm thinking about, I want to find the probability of A, but I'm going to break it down into two parts, right? So the first part is this crescent moon, right? So that is everything that's in circle A and outside of circle B, or not in B, which not being in B is B complement. And you can kind of, I'll give you another visual. I think I have another marker. Here it is. Right, if you think about where is B complement is anything outside of circle B. So you can kind of see, where does B complement intersect with A? It's going to be that crescent moon area, right? That's where there's both red lines and kind of these green lines. Right? The other component that made up circle A was this space right here, which I already showed you a visual of. That just represents everything that's in circle A and in circle B. So if I add these together, that completes the entire space and gives me the probability of A. So I've just broken kind of that circle of A down into two components. Okay. So now if I think about, let me pull this back up here, and I'll go back in a second. But notice the probability of A and B complement, that's just right here, plus the probability of A and B, that's right here. That's why those two things add up to give you that total of the probability of A, right? That's where that comes from. So if you're kind of drawing this in there, I'll kind of leave this here. Right? Any questions on that? Is that making some sense, or at least we're kind of seeing where these things are coming from? Okay. All right, so we already went through this. Told you about the intersections here. We'll talk about a few probability laws to kind of close out the rest of the class here. So one of them is that order doesn't matter, okay? So if I write the intersection or the union, it doesn't matter if I say A and B, or if I say B and A, right? Or A or B, or B or A. Think about it this way. If I say, what's the probability that someone has brown hair and blue eyes? It's the same thing as what's the probability they have blue eyes and brown hair, right? It doesn't change at all. Right? The ordering doesn't matter, right? And we'll use this a little bit when we talk about the multiplication rule on Friday, right? So order doesn't matter. The next one, or I don't know, I had this kind of slide in there. Maybe I thought it was funny at one time. So, right, when we think about intersections, sometimes we'll have large intersections, sometimes some lower ones. So the other rule that I thought I was going to is going to be this complement rule, right? So if I want to find the probability of a complement, that's just 1 minus the probability of the event. So why does that work? Well, if I think about my entire experimental outcome space, that represents an area of 1. So if I take the probability of A and I add that to the probability of A complement, that fills out the entire experimental outcome space. So I know those two things add up to 1. So if I take the probability of A and I add to it the probability of A complement, well, that should fill out the entire experimental outcome space of 1. So if I just rearrange things a little bit, subtracting A from both sides, that's how I get that the probability of A complement is just 1 minus the probability of the event. That's where that complement rule comes from. Okay. Any questions on that? And vice versa, right? If I know the complement, I could find the probability of the event by taking 1 minus the complement. And like these events A and A complement, there are going to be things like, what's the probability someone's over 65? What's the probability they're, 65 or younger, right? It's going to be kind of complete the entire experimental outcome space, right? Or in that example, it fills out every possible age that it could see, okay? So we've got this complement rule. We've got that ordering doesn't matter. The next one we're going to talk about is the addition rule, okay? So the addition rule says, if I want the union of two events, right? I want A or B, right? The probability that A or B occurs. I can take the probability of each event, add them up, but then if I've taken the probability of A, added that to the probability of B, well, I double counted what's in both of them, right? So if I've double counted it, what's one way I can account for that? Well, I'll just subtract it out once. That way I've only counted it one time. So if I take the circle, the probability of A, add that to the circle that represents the probability of B, but I have to subtract out what I double counted, which is the probability that I'm in both of them. So that's kind of where that comes from. That's one way of thinking about it, and that's to me the way that always makes sense. If I take circle A, circle B, I've got to subtract what was in both of them, right? So probability of A plus the probability of B, subtract out the intersection. Right, what's in both of them is the intersection. Okay. So if I'm thinking about this in a slightly different way, I can actually end up with the same result. So notice here, if I wanted this crescent moon, I could find that by taking everything that's in A and subtracting out the intersection of A and B. That would give me this kind of left crescent moon. Yeah. So that's basically take the probability of A, subtract out the intersection, and I'll have this crescent moon over here. So remember, this entire white space represents the union of the two events. So I'm just breaking this space down into the 3 parts. The other part is this crescent moon over here on the right, and that's everything that's in circle B, but subtract out the intersection. So add in the probability of B, subtract out the intersection of the two events. So I now have this right crescent moon, this left crescent moon. What's in between? Well, that's just add in the probability of being in both of these. Now I've got the 3 components. I added them all up. Notice these things cancel. I rearrange things a little, and I've got exactly what I had in the previous slide. So it's just thinking of this in a different way of how do we end up with this result, which is I just add up the 2 probabilities and subtract out the intersection. You can break it down into these 3 parts and then kind of see that things cancel and end up with the same equation I showed you before. Right? Or you can just think about it. I'm adding up these 2 spaces and subtracting out what I double counted. What would have been double counted? Whatever was in both events. Okay. Any questions before we keep going here? Okay with this? So how do we look at this on our contingency table? So I want to find the union of 2 events, A and B. I just said that I can take the probability of each one and subtract out the intersection. So here, how would I find the probability of A and the probability of B? Just look at the, so that would be the probability, sorry, I probably should have said this a little bit. How do I find the probability of A? No one has any idea. How did I say you find the probability of the events? You just go over to the total column, right? So the probability of A is 0.6. What's the probability of B? 0.5. So I'll add those 2 together, but then I have to do one more thing if I want to find the union. Subtract out what I double counted. What did I double count? The intersection. So the intersection of A and B would be 0.4. So I'll add up the probability of the 2 events, 0.6 and 0.5, and then subtract out the intersection, which I can get from one of those top 4 left cells. Okay. So one thing here, if I forget to subtract out the intersection, I can kind of be reminded that I forgot to do something. So let's say I forget about subtracting out what I double counted, and I just added up the probability of A to the probability of B. What would that be here? 0.6 plus 0.5 is 1.1. Why doesn't that make any sense? Remember, we're still trying to find probabilities. They have to be somewhere in between 0 and 1. So if I found that, well, I did something wrong. Oh yeah, I forgot to subtract out what I double counted, or subtract out what I double counted. So I'll subtract out that 0.4. Now I get 0.7. It makes a little bit more sense. Okay. Excuse me. Any questions on that? So that's one way of using the contingency table. I'll show you another less technical way and give you some support for why it works. So you could also, if I want the union of two events, A or B, I could just find the intersection, make an L, and if I add these up, it'll give me the union. So notice if I want the union of A and B, I go to the intersection of A and B, make this L, 0.2 plus 0.4 plus 0.1, adds up to that 0.7. Right? I get the same exact answer. Why the hell does that work? Right? So why that works is because if I'm thinking about two events A and B, so here, make this a lot bigger, make it easier to see. Got A and B here. I'm going to break that union down into three components again, but I'm going to write them a little bit differently than before. So if I want to find this crescent moon here, that's everything that's in circle A and not in circle B. So and B complement, right? What's over in this crescent moon over here? Well, that's the probability that I'm in circle B, but not in A. So that's the probability I'm in circle B and not in A, or in A complement, right? Not in A and A complement, it's the same, two different ways of saying the same thing. And then what's in the middle here? Well, that we've already said is just the probability of what? A intersection with B, or A and B. So I've broken this down into three intersections. Oh, that was off the screen, sorry. I've broken this down into three intersections, right? If I just add those all up, I'll have the entire space, which represents the union. Not the entire experimental outcome space, but the entire space within these circles, right? So notice, what's the probability of A and B complement? Right here, plus the probability of A and B, which is right here, plus the probability of B and A complement, right? So that's why, like, going to the intersection and making the L, that's why it works, right? Because the way this contingency table is set up, what it's really doing is you're picking up these three different components of the union that you want, okay? Yeah, not the most technical way of remembering it, but, you know, and also kind of remembering the rule. I always think this way is easier. Like, I just think it's really easy to go find the totals real quick and then subtract out the intersection. That just always made more sense to me. But I know that some other people like thinking about that L way and then breaking it down into three parts. That also kind of connects with them a little bit more. So I always kind of go through both ways. Okay. Any questions there? No? All right, so we got a definition now that we'll talk about, which is the idea of two things being mutually exclusive. So we'll use this kind of moving forward. It also makes life a little bit easier for us. But anytime we say two things are mutually exclusive, all we're really saying is they can't happen at the same time. Okay. So this would be something like, you know, what's the probability that someone is older than 60 and younger than 20? I mean, the probability is zero. It can't occur, right? It's a physical impossibility. So if two things are mutually exclusive, we would say that the intersection, the probability those two things happen at the same time, has to be zero. Okay? That makes our addition rule a little bit easier because now I don't have anything that I've double counted, right? If I think about what this looks like on a contingency table, I'd have a zero, right? the intersection of these two events is equal to 0. Visually, I have these two events where there's no overlap, right? That would mean they're mutually exclusive. They cannot happen at the same time, okay? Not too bad. So we'll use this terminology moving forward. So I always kind of give the example, right? Phone and internet access in the 90s were mutually exclusive. You have one phone line. I'm sure you guys are young enough now. You don't, hopefully didn't ever have to experience like your parents yelling at you to get off the internet so that they had a call from work coming in or something like that. Anyways, so we will pick up here on Friday. We're going to kind of combine some things about the complement and the addition rule. We'll look at conditional probabilities and the multiplication rule. And I will try to at least start looking at how we come up with probabilities based off of a data set in Excel, okay? So remember that online quiz, I'll get that posted as soon as I'm back to my office. That's due before we meet Friday. If you have any questions on those two, Excel and Connect homework, please reach out. Otherwise, stay safe out there, and I will see you on Friday.